In 1946, a French locomotive rolled onto a dynamometer test track and produced numbers so extraordinary that the engineers recording them assumed their instruments had malfunctioned. They ran the test again. The readings held. A steam locomotive, built on principles first proven in the early 1930s, had just delivered a thermal efficiency that diesel engineers in the 1980s would still struggle to match. The man responsible had been fighting his own employer for over 2 decades. His name was André Chapelon, and what he achieved with steam power remains one of the most systematically buried engineering triumphs in railway history. To understand how a 1930s mind outpaced 1980s technology, you have to understand what steam locomotive design looked like before Chapelon tore it apart. By the late 1920s, most railway engineers treated locomotive design as a mature craft. You made the boiler bigger, you made the cylinders wider, you added more driving wheels. Brute force, the Paris-Orléans Railway owned a fleet of Pacific-type locomotives, 462s, that were considered adequate but unremarkable. They struggled on the grades south of Paris, losing time, burning excessive coal, and requiring constant maintenance. Nobody questioned the fundamental design. The engines were simply regarded as the best that current technology could offer. Chapelon questioned everything. Where others saw a finished product, he saw a thermodynamic disaster. Steam was being generated in the boiler at high pressure and temperature, then strangled, cooled, and wasted at virtually every point between the boiler and the exhaust. The steam passages were too narrow. In the valves restricted flow. The superheater was undersized. The exhaust system created back pressure that choked the very fire that fed the boiler. The locomotive was at war with itself, and nobody had noticed because nobody had done the mathematics. Chapelon did the mathematics. In 1929, he was given permission to rebuild a single Paris-Orléans Pacific, number 3566. What emerged from the shops was externally almost identical to the locomotive that had entered, but internally it was a different machine entirely. Chapelon had redesigned the steam circuit from first principles. He enlarged and streamlined every passage that carried steam. He fitted poppet valves that opened and closed with surgical precision instead of the crude piston valves that fought their own motion. He installed a Kyle-Chap double exhaust that drew gases through the boiler tubes with ruthless efficiency, dramatically improving the fire's intensity without increasing coal consumption. And he applied compound expansion, using the steam twice, first in high-pressure cylinders, then in larger low-pressure cylinders, extracting energy that every other locomotive simply threw away through the chimney. The results were not incremental, they were violent. The rebuilt 3566 produced nearly double the power of its unmodified sisters on the same coal consumption. On test runs between Paris and Bordeaux, it hauled heavier trains at higher speeds while burning less fuel per ton-mile than locomotives twice its nominal rating. Drivers who had spent their careers nursing underpowered machines suddenly found themselves with a locomotive that pulled like something from the future. The specific coal consumption dropped to figures that made the railroad's accountants recheck their ledgers. One locomotive, rebuilt, not new, was outperforming everything on French metals. The Paris-Orléans Railway authorized more rebuilds. Each one confirmed the pattern. Chapelon wasn't lucky. He was right. Through the 1930s, Chapelon refined his methods further. He rebuilt 480s into compound machines that developed over 3,000 indicated horsepower from a locomotive that weighed barely 100 tons on its drivers. The power-to-weight ratio was staggering. These were not massive American behemoths with 14 driving wheels and fireboxes the size of small rooms. These were elegant, efficient machines that extracted more work from each kilogram of steam than anything else on rails. The thermal efficiency of Chapelon's best 1930s compounds reached 12%. That number sounds small until you realize that a typical locomotive of the era managed 5 or 6%. Chapelon had doubled the efficiency of the steam locomotive without increasing its size, weight, or complexity in any dramatic way. He had simply stopped wasting energy. And then came his masterpiece. After the Second World War, the French National Railway, the SNCF, gave Chapelon a wrecked 3-cylinder 482 and told him to rebuild it. What he created was the 242A1, a 4-cylinder compound 484 that remains, by virtually every measurable standard, the most efficient steam locomotive ever built. On test, in the 242A, one developed over 5,500 indicated horsepower. Its thermal efficiency touched 14%. It could sustain speeds above 150 kilometers per hour with heavy trains. The specific fuel consumption was so low that it rivaled early diesel-electric locomotives on a cost-per-ton-mile basis, machines that were supposedly the future of rail traction. The SNCF scrapped it after barely 3 years of service. They ordered Chapelon's detailed blueprints sealed. They cancelled every further development program he had proposed. The reason was not technical failure. The reason was policy. France had committed to electrification and dieselization, admitting that a steam locomotive, refined through principles established in the 1930s, could compete with or exceed the performance of modern traction, on many routes was politically and institutionally unacceptable. The 242A1 was not defeated by a better machine. It was defeated by a committee. Now fast forward to the 1980s. A new generation of engineers scattered across Argentina, South Africa, Britain, and the United States began asking a dangerous question. What if Chapelon had been right? What if steam traction, properly engineered, could compete with diesel power in specific applications, particularly in countries with abundant coal and expensive oil? The answer they found was humbling. Livio Dante Porta, an Argentine engineer who had studied Chapelon's work obsessively, spent decades applying and extending Chapelon's principles on working railways in South America. His modified locomotives achieved fuel savings of 30 to 50% over their unmodified counterparts. In Britain, the engineer David Wardale traveled to South Africa in the early 1980s to rebuild a Class 25 NC 484 using Chapelon Porter principles. The result, nicknamed the Red Devil, demonstrated a 28% improvement in power output and a significant reduction in coal and water consumption. It worked. The thermodynamics were sound. But here was the painful discovery. When engineers in the 1980s tried to replicate Chapelon's most advanced work, particularly the precise steam circuit geometries, the compound expansion systems, and the sophisticated valve events that made the 242A1 so extraordinary, they found that the manufacturing precision required was at the very limit of what contemporary workshops could achieve. Chapelon's 1930s designs demanded tolerances and craftsmanship that the steam era's best artisans had delivered almost intuitively, but that modern shops, tooled for diesel and electric work, could barely reproduce. The institutional knowledge was gone. The specialized tooling had been scrapped. The skilled boilermakers and fitters who had built Chapelon's compounds had retired or died, and their expertise had never been recorded in any manual. The 1980s engineers were not failing because Chapelon's ideas were outdated. They were failing because the industrial ecosystem that once supported that level of steam engineering had been deliberately dismantled. The knowledge existed on paper in Chapelon's meticulous calculations and drawings, but translating those drawings into metal required a chain of skills, tools, and institutional experience that had been broken. In the United States, the ACE 3000 project attempted to design a modern coal-burning steam locomotive for freight service. It drew heavily on Chapelon's thermodynamic principles. The project attracted serious investment and engineering talent. It never produced a working locomotive. The gap between theoretical design and practical manufacture proved too wide to bridge within budget and schedule. The irony was devastating. A French engineer working with 1930s metallurgy, 1930s machine tools, and 1930s manufacturing techniques had produced results that 1980s technology, with all its computers, modern alloys, and precision machining, could not replicate. Not because the physics had changed, not because the designs were flawed, but because the human infrastructure in the living chain of knowledge and skill that connects a blueprint to a finished machine had been severed. André Chapelon died in 1978, largely forgotten outside a small circle of devoted followers. He never saw the 1980s revival attempts. He never saw engineers from 4 continents struggling to recreate what he had achieved in the workshops of the Paris-Orléans Railway, with slide rules and intuition. His life's work proved something that extends far beyond locomotives. It proved that technological progress is not a straight line, that knowledge, once abandoned, does not wait patiently to be rediscovered, that an entire discipline can leap forward by decades through the work of a single brilliant mind, and then lose those gains completely when institutions decide the future lies elsewhere. The 24201 is gone. No replica exists. When the blueprints were eventually recovered from SNCF archives, but the locomotive itself was cut apart for scrap in 1960. What remains are the test results, the calculations, and the stubborn, documented fact that in the 1930s, one man made steam do what the world wouldn't believe for another 50 years. And when the world finally came looking for his secrets, it discovered that brilliance, without continuity, is the most fragile thing in engineering.